Hello everyone, welcome back to another session. In this session, we are going to study about the probability of error in binary frequency shift keying. And the probability of error is always dealt with respect to the receiver side. So we have here the receiver part of the binary FSK. As we have already studied in the previous video, how to perform the coherent detection of binary FSK. So basically this receiver has the two correlators, namely upper correlator, lower correlator, or top correlator or bottom correlator. And the input is the received signal, which is a sum of the transmitted BFSK signal and the additive white Gaussian noise W of t. So the BFSK signal S of t is different for different symbols. For example, for symbol 1, the BFSK transmitted signal is given by S1 of t, which is square root of EB by 1 of t. And for symbol 0, the BFSK transmitted signal S of t is given by S2 of t, which is square root of EB into pi 2 of t. So therefore, for both the symbol 1 and 0, the received signal x of t is given by S of t plus W of t. If you transmit the symbol 1, then the received signal x of t becomes S1 of t plus W of t. And for symbol 0 to be transmitted, the received signal x of t becomes S2 of t plus W of t. So, where the W of t is additive white Gaussian noise, and we know that it has zero mean and its variance sigma square is equal to n naught by 2, which is nothing but power spectral density of additive white Gaussian noise. Now we have the input as received signal x of t. We have to calculate what are the outputs of these two correlators, top correlator as well as bottom correlator. So now first let us calculate the output of the top correlator, which is denoted by x1 as, so x1 is equal to integration from 0 to td x of t into pi 1 of t into dt. And we know that when the symbol 0 is transmitted, the received signal x of t is given by S2 of t plus W of t, where S2 of t is the BFSK transmitted signal when symbol 0 is transmitted. Now let us make use of this x of t in the integration in order to get x1. So x1 is equal to integration from 0 to tb. X of t is S2 of t plus W of t, which is multiplied by pi 1 of t. Let us simplify this one. So we'll get 0 to tb integration S2 of t into pi 1 of t dt plus integration from 0 to tb W of t into pi 1 of t into dt. And as we know that according to Gram-Schmidt orthogonalization procedure, whenever you integrate the product of the signal and a basis function, you will get the coefficient or the element of the signal S2 of t. So here we get S2 1, which is the element of the signal S2 of t. Similarly, plus if you integrate W of t into pi 1 of t, you will get W1, which is a random variable, that is the output of the top correlator when the input is W of t. And here in the first integration, the output of the correlator is S21 when the input is S2 of t and pi 1 of t. So x1 is equal to, we get S21 plus W1. And if you see in the previous video, the constellation diagram, so in the constellation diagram, we have two message points, which are S11 and S22. where S11 and S22 both are square root of EB, right? Because the amplitude and energy content remain same irrespective of whether you transmit a binary 1 or 0. So here S21 and S12, these values are 0 except S11 and S22. So x1 is equal to 0 plus W1. So this is the output of the top correlator. Once you calculate the output of top correlator, in order to find the error probability, we need to have the conditional probability density function where we require the mean value as well as the variance value. So how to calculate the mean of this random variable? This x1 is the random variable which we got at the output of the top correlator. So now let us calculate the mean of this one. So mean is nothing but expectation of x1 is equal to expectation of 0 because x1 is equal to 0 plus w1. So it is 0 plus w1. Expectation of 0 is 0 and the expectation of w1 is a noise and noise has always 0 mean. So 0 plus 0 is 0. So the mean or expectation of x1 is 0. Similarly, let us find the variance of its random variable x1. So variance of x1 is equal to 0 plus w1 and variance of constant. Please remember the variable of constant is always 0 and the mean of the noise is 0. So variance of the noise constant is 0 and the variance of noise, additive white Gaussian noise, is nothing but power spectral density which is given by n naught by 2. So variance of x1 is equal to n naught by 2. So once you calculate the mean and variance of the output of top correlator, let us find what is the output of the bottom correlator when symbol 0 is transmitted. So the output of bottom correlator is given by x2. Similar way you have to calculate. Only change is the output of the bottom correlator. That is, in the bottom correlator, the pi 2 of t is get multiplied with the received signal. In the previous top correlator, the pi 1 of t gets multiplied with x of t. Here, pi 2 of t is going to multiply with x of t. So again integration 0 to td, s2 of t plus w of t pi 2 of t. Simplify. So in the first integration gives you s22 plus, and the second integration when input is w of t gives w2, right? And we know that s11 and s22, this s22 is located on the vertical axis, that is pi 2 axis. So it is square root of ep plus w of t, right? So now let us find the mean and variance of this bottom correlator, that is x2. So mean of x2 is given by square root of eb because the expectation, this is a constant, right? And this is w2 is the additive white noise. Mean of this noise is 0 and the expectation of constant is the constant only, that is square root of eb. So now variance of this one is x2 is equal to the variance of constant, this square root of eb is 0 and the variance of noise is its power spectral density m naught by 2, right? So once you calculate the mean and variance of uh, x1 and x2 individually, so now let us apply those random variables to the subtractor, and at the output of the subtractor you will get a new random variable which is L, that is x1 minus x2. So now you have to also find the mean and variance of this, the new random variable which is x1 minus x2. So how to calculate that? Mean of, that is expectation of L, is equal to expectation of, take the expectation on both the side, expectation of L is equal to expectation of x1 minus expectation of x2. And we have already calculated this expectation of x1 and expectation of x2. So expectation of x1 is 0 minus expectation of x2 will be square root of eb. So what you will get is expectation of L is equal to square root of minus minus square root of EB. Similarly, we'll calculate the variance of this new variable L, that is variance of x1 plus the variance of x2. So I supposed to take a negative here minus, but I have taken positive. The only reason is the variance of random variable L is independent of which binary symbol was transmitted, right? So if you transmit 0 or 1, irrespective of the symbol which is transmitted, the variance of the variable L is remains fixed. That's why I have taken here plus, right? So variance of x1 plus variance of x2, and both are n naught by 2 each. So when you add n naught by 2 and n naught by 2, you will get n naught, right? And before we calculate or to measure what is the probability of error, we should know the conditional probability density function when symbol 0 is transmitted. Understood? Because initially we started our discussion by assuming the symbol 0 was transmitted. So we have to calculate the conditional probability density function when symbol 0 is transmitted, right? So FL of L comma 0 means it is the conditional probability density function of L when 0 was transmitted. The standard expression considering the noise as Gaussian distribution, right? So it is 1 divided by square root of 2 pi variance of L, right? Variance is denoted by what? The square of standard deviation, right? The sigma is nothing but standard deviation. The square of standard deviation will be variance into exponential of minus L minus mean whole square divided by 2 times variance, that is sigma square. So now let us substitute the values of mean as well as variance of L. So it is 1 divided by square root of 2 pi. Sigma square variance of L is equal to n naught into e raised to minus L, and here mu is E of L is nothing but minus square root of EB. Minus into minus becomes plus square divided by 2 into n naught, right? So in the denominator here we have 2 into n naught. So if I make it square root of 2 into n naught, then we can take whole square for both numerator as well as denominator. So that is what I have done here, whole square, by taking square root of 2 by n naught in the denominator, right? So now after doing this, we have to have uh, the error probability. How to calculate the error probability once you know the conditional probability density functions, right? So when error occurs, the probability of error is calculated only when some errors occurs in the receiver side, right? So error occur whenever the symbol 0 is transmitted, but when you make a decision in favor of symbol 1, the symbol which is transmitted was 0, but the decision is made in favor of symbol 1. So definitely the error has occurred. And what is the probability of that error, that we have to calculate here, right? So since symbol 1 is decided in the receiver side, so symbol 1 means it is a region 1. If you see the constellation diagram, you will come to know that is a message point 1 lies under region Z1, where the region constraint between 0 to infinity is. So error probability when 0 is transmitted and 1 is made a decision. So it is integration from 0 to infinity FL of L comma L bar 0. That is conditional probability when 0 is transmitted dl. So 0 to infinity, substitute this conditional probability density function from equation number 3, right? So after substituting, let us integrate, right? So just to make ease of integration, we will make some substitution for simplification, e.g. Z is equal to L plus square root of EB divided by square root of 2n. So this I will make as a Z, and will have the expression for this variable dl. So that becomes a dz into square root of 2n naught. I'm not going to explain in detail this, as you already studied how to make substitution, how to simplify, how to transform the limits from x to z, right? So I will not explain much on this. So we'll get limits square root of eb by 2n naught to infinity. Means limits change from 0 to infinity to these new limits, and dl is dz into square root of 2n naught. So just simplify this one. You will get 1 divided by square root of 5 integration from this term to this infinity e raised to minus z square into dz. So it is, let us make some adjustment here, substitution. 2 divided by 2, so that this becomes square root of eb divided by 2n naught e raised to minus z square dz. And we know that a complementary error function, which is widely used function in error uh, reduction or minimizing the probability of error. So that is ERFC of u is equal to 2 divided by square root of 5 integration u to infinity e raised to minus u, right? And if you compare these two equation number 5u, we can write equation number 4 as PE of 0 is equal to 1 by 2 ERFC of square root of EB by 2n naught. So this is the probability of error when 0 is transmitted and the decision is made in favor of symbol 1. So now let us, similarly, we can calculate the probability of error for the second kind. Second kind means when you transmit symbol 1 and at the receiver side decision is made in favor of what? Symbol 0, right? And that is also same because we know that the the transmission of zeros and ones are considered as equiprobable, right? So P of 0 and P of 1 is equal to 1 by 2. So the average probability of error is calculated as in the previous base key. So finally we will get P is equal to 1 by 2 ERFC of square root of EB divided by 2n naught, right? We just compare the error probability equation for BPSK and BFSK. Only difference is what? In BPSK we have only EB by n naught inside the square root. Here we have EB divided by 2n naught. So this is about how to calculate or how to determine the error probability expression for the coherent binary FSK. Right? Hope you understood this concept. Thank you.